And I'm here with Gav, the Mechatronics Guy. You've seen Gav before, and he's going to show us what he's been working on.
My obsession recently has been polarized light, and I've been off and on this one for a couple of years. So I've been playing around with polarized light, and I really, really love it, and it's a really interesting kind of polarized light is all around us, and we can't see it, and that frustrates me. I think it's rude. So this is a modification I made of something made by David Prucci, who won the Hackaday Prize a couple of years ago for the Dolpie polarization camera. And it's using some LCD shutters that I've modified and put extra layers on. These are LCDs from shutter glasses, like 3D.
Sorry,
yeah,
so
yeah.
they're one plane. They're just
one pixel.
Right.
And what you can kind of model them as a voltage controlled wave plate. We'll get to that later. But if we, I don't know if we can shoot through here and look at the tables.
We'll try it. Let's give it a go.
So this is just an ordinary scene with some tables. And if we put this in front.
They're pulsating.
And it's not, we're not looking at particular mirrors or anything. This is just sheen on just plastic table or grass that's a little bit damp, or these tiles, and it's totally changing the polarization, having done that bounce from the sky to us. And in the same way, everything we look at is slightly not quite perfectly polarized. So we get information there that we just totally can't see normally. And our second example for that is if we look through the circular one. So the circular one's not really doing much.
No.
You can see a little bit of a flash there. That might be more to my device being a little bit imperfect about the rotations around the sphere it's doing. But if we go and look at the table, so if we look at the stuff on the table,
we can see one of the lenses.
Why is it not flashing?
It wasn't flashing before when I was looking through it.
There we go.
Oh, there we go. Because you're alternating the...
That's it. Right hand circular, left hand circular, right, left, right, left, right, left. And that's how the 3D cinema works. It's got to do that, you know, like 40 times a second or whatever. There's different ways, like people know light can be polarized, but there's actually really different ways that it can be polarized. So if you consider light does stuff to electromagnetic, let's say the electric field, and if it's coming in, it could grab a charged particle and kind of move it up and down. And if it's moving up and down, we'll call that vertically polarized. And if it's left and right, we'll call it horizontally polarized. But you could just as easily have it diagonal, so 45 degrees, or anti-diagonal minus 45 degrees. But it's also possible if you've got something that's got a horizontal and a vertical component and they're a little bit out of phase, that you'll have something that produces circular polarization. So right-hand circular polarization, left-hand circular polarization. If you sort of think about all the ways these can come together, there's a model called the Poincare Sphere from Mr. Poincare. And here's a tangible version I built of it. This is to get it straight in my head that, you know, what's going on and what do optical components do to this. So for example, you can have light that's perfectly horizontally polarized, and that'd be this point on the sphere, or it could be perfectly vertically polarized, and that'd be that point on the sphere. And what a lot of complex optical things do, like wave plates and linear filters and sugar rotators and Faraday rotators and things like that do, is actually just a rotation on this sphere. So as an example, if I get a wave plate and I drop it on there, what that actually does, this can convert horizontal light into circular light. So if I start off horizontal and I put my wave plate at 45 degrees, then that would turn horizontal light into right-hand circular polarized light. And it would turn vertical light into left-hand circular polarized light.
So this is just a way to visualize the rotational aspects of the light.
And this might seem a little bit weird why I'd want to do this. Because it's pretty straightforward if you're just looking at one element of a filter. But when you're looking at a whole bunch of filters or a whole complex optical system, suddenly it gets very complex quickly. And I wanted something to just tangibly show me what was going on. And so that's a wave plate, so that's one common optical component. Another thing you can have is if you put sugar and you shoot light through a sugar water solution, it's actually going to do a rotation around this axis. And ordinary biological sugar that we you're sort of used to is all right-handed sugar. So it actually does a right-handed rotation, which is doing that around the sphere. So horizontal light through a sufficient thickness of sugar water would become diagonal light.
So you just have to dissolve it in water, and that's enough to do it.
And you could tell the difference between lab synthesized sugar and biological sugar because the lab synthesized one's going to have an equal mix of left and right-handed, and on average it's going to do nothing.
Right. Oh, okay.
Yeah.
Right. So it has no aspect to it.
No net rotation. But here's the interesting thing. You could make right-hand sugar in a lab, but you'd have to have something that was already right-handed or of one particular handedness as a catalyst. You couldn't start from nothing and get a net asymmetry in the amount of handedness there. You'd have to use some catalyst which is already, or some runaway reaction, and then it'd be a 50-50 crapshoot of which handedness you got.
So what is the raw sugar if you just got it out of the cane?
Just out of the cane, it'd be right-handed. Right-handed sucrose is levosucrose. Levodextrose? Sorry, dextrose. That's why it's called dextrose. It's dexter. It's dextrose. Yes.
Right.
And artificial would be levo. Levodextrose, L-dextrose, whatever. The chemist is probably going to call me out on that, but it's close enough. And in the same way as the sugar does a rotation, you can make a Faraday rotator, which is, Ben Kress now made this with olive oil and a solenoid, and you can change the direction of the applied field, same axis, and it'll do the same rotation. But that one because you can flip the magnetic field, you can actually make it go in the other direction. So these are three models of what three common things you might find in a lab due to the polarization of light. I made another model of this conserved quantity because the amount of horizontalness squared plus the amount of diagonal squared plus the amount of right-handedness squared equals 1, which is why it's a sphere, which is why it's this conserved quantity. So unless you have a filter that throws away amplitude, you're not actually going to do anything to the amplitude there. It's just going to be conserved. As a mathematicians call this set of things SO3, special orthogonal group 3. But
every filter is going to have attenuation.
A teeny little bit of attenuation.
Right. Okay, so that doesn't matter too much.
No. Okay. Or in this, a wave plate, a Faraday rotator, and a sugar rotator, you can all find kind of close to ideal versions of those that don't throw any amplitude away. Right. Something like a polarizing filter, on the other hand, will throw away 50% of the light, and that's kind of just going smoosh to one side of the sphere.
It throws away 50%? Is that an inherent nature?
An inherent nature of everything that comes out is, I think it's the likelihood that it'll get through is the cosine squared of the angle, something like that.
Got it.
Now this is the Poincare Sphere, which is for polarizations of light. And I made a similar model called the Block Sphere here. And this is another structure which is SO3. It's a conserved quantity under rotation. And this is a qubit. So this is a qubit with a 0 state, a 1 state, and because probability amplitudes are complex numbers, I won't get into that, but they're a complex thing, you can have a plus, a minus, a plus I, and a minus I as the 4 combinations there. Mm-hmm. And these are actually kind of equivalent to each other under certain circumstances. And it actually makes a lot of sense if you're thinking about doing quantum computing with photons, because a photon is often called a flying qubit. So that's the Block Sphere, and that was the background of sort of thinking about these quantities and working with them. But what the wave plate does is really cool, because it's doing this rotation there. And there's a device called a Polarization Controller that looks like this. So it's 3 wave plates, one after the other. Oh, should I explain about what a wave plate is?
Yes, please.
Yeah. I should explain what a wave plate is. So if you get like a mineral like calcite, it's what do you call it? Anisotropic. It's different. It has a preferred direction of, like the crystal structure is aligned in one direction, which means that it because it's more dense going this way than this way, it has a slightly different speed of light going polarized this way versus light polarized this way. And if you were to cut a calcite crystal to a certain thickness, then the light that's coming in, say it was diagonally polarized, that's got a little bit of a component in the vertical and a little bit of a component in the horizontal. So those two things go through the crystal. One of them, they're split into two different ways to traverse. They're on 2 travelators, and one travelator is going faster than the other. Right. So by the time the crowd recombines, there's a phase shift between those 2 waves. And your horizontal and vertical are now out of phase, and your diagonally polarized light is now doing a circular. So you can use a wave plate, usually a quarter wave plate is the most common one, and that'll convert linear light into circular light. And this is actually what frustrating is, because if you say to a lot of physicists, like, what does a wave plate do? And they go, a wave plate converts linear light to circular light. It's like, no, it doesn't. It really doesn't. It can, but if we jump back to the Block Sphere, the Poincare Sphere, so this is most definitely converting, say, vertical light into right-hand circularly polarized light, if we do that, right? Mm-hmm. But what if I put in light that was diagonally polarized? It's not going to do squat because its axis is lined up with the axis of the wave plate.
Right.
And so there's actually always going to be 2 points where it does absolutely nothing. And it'll convert, and it does kind of lesser conversion. So if you had a little bit diagonally polarized and a little, mostly diagonally and a little bit vertically polarized, and you do a rotation, it'll be still mostly diagonal, but it'll just be a little bit right-hand circular polarized. So it'd be elliptical. And so it's like I really wanted something to visualize what's actually going on with this. Because if you jump back to that polarization controller, actually these things are really cool. The actual implementation of this, you usually achieve this in a lab. Dave, I don't know if you can do like a Google image search and throw a photo on top of the...
I'll try.
Is if you look at a polarization controller, it's just, you feed in a single mode optical fiber through coils, and because you're coiling it up and it's just stressing it a little bit, it's affecting the polarization. So all you do, it's just a fiber going through a loop, and then another loop, and another loop. And it's stressing the fiber a little bit and affecting the polarization the same way that the crystal does. Got it. And so all you do is you rotate the paddles around. It's just 3 paddles, and you just go swivel, 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 and you can turn any polarization state into any other polarization state.
I've seen them. You can actually buy them, and they physically rotate. They physically move. It's
just ordinary fiber, single mode optical fiber.
Right. Any single mode fiber.
Any single mode fiber that you stress, I believe, will do that. I don't think it has to be polarization maintaining fiber or anything. I think it can't be polarization maintaining fiber. Do you know the magic about what single mode fiber is?
You're going to tell us.
So if I go over here, is that all right? Yeah. So these tiles over here, if this was a canal, and we had waves coming along through there, because this canal is like really, really wide, it could support waves going this way, but it's wide enough that it could slightly support waves going that way. So you could have any pulse that came through here would kind of be reflected more than once. And there are multiple possible ways for the amplitude coming in to get to the amplitude coming out. But if you make the channel narrow enough, like this grating drain here, so that it's much smaller than the wavelength of light, it's not just hard, it's impossible for light waves to exist at that dimension. There are no modes that support oscillation. So the only way that this grating could possibly oscillate would be straight down the bore, meaning that single pulse in, single pulse out, and you get the minimum amount of broadening that you can possibly get compared to something much, much wider going on.
And the advantage of multi-mode, though, is that you can make use of those different.
You can do that with single mode as well. You can do that with single mode as well.
Yep.
You can send multiple wavelengths down there. The difference is how much each perfectly narrow pulse will be smeared out. Remind me to tell you about Bragg gratings and fiber couplers and how they make them, and it's basically just doing terrible things to a fiber until the signal meter goes whoop, and yeah, just like heating the fiber up until two layers are kind of cross coupling, and then it's like, yep, done that. All right, call that one done. Next one, put the next one in the rig. Yeah. Back to the fiber controller. So the fiber controller is really cool because with 3 quarter wave plates, 3 things that are doing a 90-degree rotation on this sphere, you can turn any input polarization state into any other polarization state. So if you wanted to turn diagonal into 67.2 degrees polarization, you could do that quite easily, just by manipulating those 3 paddles. I wanted a tangible model of that. So actually, first of all, this is what I made for the half-wave plate. So a half-wave plate is doing a 180 rotation on the sphere. And that's really useful because right-hand circular would convert to left-hand circular polarization. So what this is our input coordinate frame. And you can see you've got vertical, horizontal, anti-diagonal, diagonal, right-hand circular, and this is the output one, and you can see that right-hand is always turned into left-hand. And depending on which axis, at what angle you put the fast axis of your wave plate, you can just do whatever you like with the polarization. Sweet. So this is a tangible model of an actual like half-wave plate you could get in a lab. And that's really cool, but I wanted to go a little bit beyond that and do any-to-any mapping and see if I could get something tangible that you could play with.
There is a point to this in the end of what you're actually doing this all for, so let's just say that.
You, I don't know if you want to later on, I'll show you the shutter thing and you could start with that and then...
Right.
Yeah. So this is 3 quarter wave plates joined together in a physical model. And basically I just choose what I want my task to be, how I want to convert between these coordinate systems. Say I want anti-diagonal to go to vertical, and I can just kind of turn it until that happens. And actually, I've switched right and left polarization, so I'd have to play around with it a little bit more until What can I do with that?
That is great.
With some judicious playing around, you can make anything happen. And so this is a model of using those 3 plates to do anything to anything. And I've actually...
Are there any other physical models like this, like educational models?
This is precisely why I made it. I wanted to make something that you could play with, because it's like, because otherwise you're just moving 3 paddles around and it's totally unintuitive as to what's actually happening. Whereas this is, maybe it's not the easiest to work with, but it's actual, very tangible, and you can see what it physically means at each stage of the process. And I've actually done, I took a random task of turning polarization into another polarization on my website and manually manipulated it until I got it lined up as I wanted, then noted the angles of the wave plates, did the Mueller calculus on that, which is like 4x4 matrix operations, multiplying 3 of them together, then putting a 4 vector in as the input, and then looking at the output. Nice. And I got the right answer. I got like within a few % of the right answer. So I'm super happy with that. For laser cut wood and like hastily assembled, not quite 90-degree, bent aluminium, it's not too bad.
This is how they would have done it before computers came along. This is how you did algebra, like you draw.
You didn't just, before you had a digital computer, you didn't just pack up and go home. You had to do it.
Yeah, you built or drew something to model it.
This is totally different than my original idea. I originally had it as a linked thing that was more like a pan and tilt unit, and I realized that I had the arrangement backwards. So this is like 10 o'clock at night, and I'm like, stuff it, just do simple stuff. And so I like laser cut really simple ones as examples, and then just like hot glued them together and did enough of them that I was satisfied that this relationship with the gears should work, and then started to, I'm like, because at 10:30 at night I'm not really thinking on all cylinders, and it's like, all right, how can I trade off effort for thinking, and let's just laser cut it and hot glue it together until I'm sure that I'm not fooling myself what the result is. So that's, yeah.
What is the end goal?
So the end goal of all of these things that I've been playing around with is, following on from David's work with the polarization cameras, I really want to make a camera that will take a full picture of an image, and for every pixel in that image, give a sphere breakdown of where it is. Because every pixel has a different story to tell about its polarizations, and maybe it reflected off the table, or maybe it's off the sky, and the sky polarizes light subtly differently. And is it strongly polarized, in which case it's right on the edge of the sphere? Is it weakly polarized, in which case it's much closer to the origin, and the rotations don't really affect it that much? So there's all this information there which is kind of hidden in our just everyday view of things. And I really, really, really want to get a camera that can just capture that, and so I can actually start seeing that.
And you think you can do it on an individual pixel level?
Yes, absolutely, absolutely. Right. By having movable filters and things like that, and taking multiple images and then calculating to get back to the original states. As part of this, I built an optical table that can rotate filters around and characterize materials, and I'm trying to bootstrap up from the ground up. How much can I get without any known lab grade stuff? And I'm slowly getting there. But an interesting thing has been, I can figure out what vertical polarization is and what horizontal polarization is based on how light reflects off the surface of water or some known surface. But the difference between right-hand circular and left-hand circular is actually really, really hard, because I need a wave plate at a wave plate that I know which axis is the fast axis and which axis is the slow axis. Otherwise, it's like, if I have this on the sphere, it's what this does is completely different if the axis is lined up that way than if the axis is lined up that way. It's right and left is going to be completely symmetrical if I don't know which way it is. I can tell the difference, but I don't know which one is truly right-handed.
Got it. In an absolute
sense.
In an
absolute sense.
Yep.
So these things are, according to the Real 3D website and other places, the left lens is left circularly polarized and the right lens is right circularly polarized. That tells me everything, right? No, because there's two conventions that are about equally popular, whether light is coming from the source or towards the observer, as to whether it's the left and right according to that. So I still don't know. So I'm slowly building some stuff to figure that out and get my quest for left from right happening. And that's going to rely on having, I've made some stuff I made my own rhomb, Frenzel's rhomb, which is how Mr. Frenzel originally converted it. The trouble is I've laser cut the acrylic and I've got it polished, but I've introduced so much heat stress from the laser cutting that it's now completely birefringent and overwhelming. So I'm now trying to anneal the acrylic back to being optically perfect. And that's an ongoing project.
Again? No, wouldn't you start the process again?
No. I wouldn't. Sorry, I wouldn't start from scratch because if I want to shape the acrylic with a laser, I'm going to introduce stress. Or if I use a saw, I'm going to introduce some stresses as well and heating up. And so what I need to do is make it the shape that I want and then anneal it back to being completely unstressed. And I've done some experiments and like heated it up to 90 degrees, which is just under glass transition temperature, held it for several hours and brought it back down at no more than 10 degrees per hour. And I've massively reduced the amount of stress, but it's still not to zero yet. So I'm getting there. That's my quest for left from right via annealing acrylic. And yeah.
That's great.
Because I don't have any lab grade stuff that I can just look up the calibration sheet and go, oh, that's the fast axis and that's the slow axis. So yeah. Yeah.
Can you buy them?
You can. You absolutely can. Okay. But at this point, it was like a challenge of how can I do from first principles.
Are there any animals out there that are sensitive to polarized light? Have they evolved? Is there any advantage to that?
Yeah. And so the mantis shrimp, I believe, can see in circularly polarized light. There's a bunch of other underwater ones. A cuttlefish, I think, can also do it. A lot of beetles have carapaces on the back of the beetle that are preferentially right circularly polarized instead of left. Wow. And they think it's like a signal to the same species to not. So if my playing around with the acrylic and the ROM and stuff didn't work, my backup plan was to go to the museum with the glasses and look at beetles and figure out whether the beetle was brighter in this eye or in this eye. So beetles as an ISO standard calibration object is, yeah.
The ISO beetle. All right. Thank you very much, Gav. That's hugely fascinating. Good luck with the project. Maybe we can do a follow-up.
Yeah. I'll show you the optical table at some stage.
Awesome.
Because that'll all be open source and CNC controlled filter rotators and yeah.
Fantastic. Thanks, Gav.